Is my stream visible? If it is, can someone just let me know in the comments quickly? So, can people see my slides at the moment? Okay. Yep. Okay, that's great. All right. So for the first part of Math2601, we'll be covering mainly 2 topics with me, and then I'll be handing it over to another member to cover the next 2 topics. So firstly, for my topic, I'll be covering through group theory, which is only relevant to Math2601, and also vector spaces. Okay, so let's have a look. From first year linear algebra, you would have gone through some core concepts of vector spaces. Before we dive back into that, we'll look at essentially a simpler version of vector spaces called groups. Okay. So the first definition that we're going to go through is that a group is a non-empty set with an operation star defined onto it. The star can be anything. It can be like normal addition or normal multiplication or scalar multiplication and so on. And it has to satisfy 4 conditions. The first condition is that it has to satisfy closure, which means that if 2 elements A and B are in the set G, if you take A star B, it ends up in the set G again. Okay. The next condition is that you need associativity, which means that if you have A star B in brackets and then star C, it's the same as if you have B star C in brackets and then have A star out in the front. So you can interchange the position of your brackets. Okay, but be careful. This does not mean, so this one here does not mean that this is always true. Yeah, just because you can interchange your brackets doesn't necessarily mean that this is true. Okay, and then the next condition is that you have existence of identity, which means that there exists some element, let's call E, within the set G, such that when you take A star E, it is equal to E star A, which is also both equal to just A. So basically some element in the group where if you take A and then operation and then that element, it returns you back to your initial element. So for example, if we're working over normal addition, this element would just be 0, right? Because if you have 5 plus 0, that's equal to 0 plus 5, that's equal to 5, right? Like the 0 here just brings you back to the same element as before. And finally, there needs to be an existence of inverses, which means that for any A in the set G, there exists an A inverse such that A star A inverse equals to A inverse star A equals to E. So for example, again, just working over normal addition, if for every real number, the negative of that number is the inverse. Because for example, 5 minus 5 brings you back to 0, which we previously defined as being that E in the group G. Okay. And finally, those are the 4 main conditions you need to claim something as a group. There is an extra condition where if it's also met, it's called an abelian group. And this is what I was talking about before. If this thing is also true, which is, like I said, distinct from the second condition here, associativity, then you have basically a set that commutes. So A star B equals B star A. You can not only interchange the brackets, but you can also interchange the order in which you write out your expression. So A star B is equal to B star A. Okay. And usually the typical notation for a group is in brackets G and then comma star. So this would represent the set that the elements are coming from, and this would represent the operation that you're applying. Okay. So let's have a look at an example on how we can prove something as a group. Let A be a fixed integer, and let G be the set of all bijections, f from the integers to the integers, having the property that f of n plus a equals fn plus a for all n in Z. Prove that G is a group under composition of functions. So recall, we need to prove 4 things here. We need to prove that it has closure, its associativity, it has an identity, and that its inverses exist. Okay. So the first thing we're going to have a look at is closure. Let G and H be elements within G. Then, since this is the property we're working with, that would imply that G of n plus a is equal to Gn plus a. So this first line, I'm just, I guess, stating what does G and H being within G mean. So G being within G, little g being within capital G, means that G of n plus a equals to Gn plus a. That's just the same as this first line here, but I replace f of G. And secondly, that means the same thing for H. So same thing as this, but I replace the f of H. Okay. Then that means if I take G composed of H of n plus a, then I would get G of Hn plus a. So here to here, I just used this statement. Yeah. I turned Hn plus a into Hn plus a, but with the, like, I basically broke the brackets up. Okay. And then I go from this entire step here to this step here by then applying this statement, right? So if I have G of something plus a, I can break it down into G of that something and then separately plus a. So I did the same thing here. I took G of H of n separately and then took the a out, right? Let me just get rid of this. Okay. But then that means that we are in G again, because we are now in the same form as our initial property. We have some function of n plus a. We have some function of n plus a. And so since it's in the same form as our initial property, we can then claim that it is closed in the composition, because after we compose G and H together, we still end up with something that's within G. Okay. And so we claim that G is closed under composition of functions. By the way, if you have any questions, just leave a comment on the chat and I'll have a look. Okay. Now, the next thing we have to prove is associativity. That one is quite easy for this example, because in the course, it should have already been stated somewhere in the lectures that composition of function is always associative. So you can just make that claim and like it's done. Okay. The next thing is you have to prove that there is an identity. Usually to do that, I just like to claim that something is an identity and prove that it does indeed work. So in most cases, for this part, the identity is usually something that's not too hard. So for example, here, I'll be claiming it's the identity function. But for example, matrices, it's for example, usually the identity matrix, or if it's to do with vectors, it might be the zero vector or the basis vectors. It's usually something that's pretty easy. So you can usually claim that that is the identity and then just prove that it is indeed the case. Okay. So for this example, I'll be claiming that it's the ID function. So the function that basically maps something to the same thing, right? So we have to prove that if it is the identity, that A of the operation E equals E of the operation A equals to A itself, right? So that means I need to prove that ID composed of F is the same as F composed of ID is the same as just F itself, okay? So ID composed of F of n plus A, again, we apply the property of the group G to get to here. So the function of n plus A just brings you to the function of n plus A separately. And then we still have the ID at the front. But since ID is just the identity map, we get mapped to this firstly. So ID of Fn plus A, you just have, again, break it down. And then finally, ID of F is just, like I said, ID is the identity map. So it just brings you back to Fn itself. So you're left with Fn plus A. But Fn plus A, if you reverse the property given to you, is f of n plus A. And so that first part is done. So this is equal to f, right? And then second part, f of id of n plus A. We just use the fact that this is the identity map to map us to n plus A. And then that's basically done already, right? So f of n plus A, this part I guess is not really necessary. It's just to show you that it again obeys the same property, where you can break it down to fn and then separately plus A. But basically from these two steps, it's already clear that this is also equal to just f itself, right? And so finally, you can claim that id composed of f is just f composed of id, and in both cases, it's just equal to f, right? And so thus it has been verified that the identity function is indeed a valid identity element for the group G. Okay. Now the next part of this is after we have proved that an identity does exist, we have to prove that for every element there is an inverse such that it brings you back to this identity element. Okay. So number 4, existence of inverses. Firstly, as f is bijective, that means f inverse exists, because if f is bijective, it's 1 to 1, and so an inverse always exists. And in fact, not only does inverse exist, it's also always a bijective function. Okay, so we are now left with just proving that f inverse is also in G. So we know that in general, for this function f, an inverse does exist. We just need to show that this inverse also exists in the set G. Okay. So the way to go about this was I let some arbitrary m equals to f inverse of n. Okay, I start off with this. Okay. The reason I do so is just makes things less complicated, so we don't have stuff like f of f inverse of n plus a and so on, like in here. Right? I just denote m as f inverse of n first. And then we have that n plus a equals to fm plus a. Okay. And this just comes from this statement here, right? My n transforms into fm if I just bring this f inverse to the other side. Okay. But then again, by the property of f given to us, this can be rewritten as this, right? Because recall that we have this property here, right? And so we're really just reversing it this way around to get f of n plus a. Okay. Now if we apply f inverse to, let me erase some of this, to both sides of the equation here. So we apply f inverse to this and f inverse to this, then we get this equals to this, correct? F inverse of n plus a equals to f inverse of f of n plus a. But f inverse of f would just reduce back down to nothing, and so you're just left with n plus a. So you have f inverse of n plus a equals to n plus a. We're just left with this side, this part inside, right? But recall that m we previously defined as f inverse of n. So again, we replace that with f inverse of n plus a. And as you can see, we have f inverse of n plus a equal to f inverse of n plus a, which again satisfies this property here. We have some function of n plus a equaling that function of just n, and then separately you add a. And so again, we have shown that f inverse not only exists because of this, but we have also shown that it lies also in the group G. Okay. And so indeed, G is a group under the composition of functions because we have satisfied all 4 conditions. Okay. Okay, good. Next thing we're going to have a look at is the properties of groups. So from the base definition of groups, we can have some basic properties that we have been accustomed to. So firstly is that the identity and the inverse are unique. So for every element, if there's an inverse, that inverse is unique. And for every group, when you define an identity, that is also unique. And second dot point is A inverse just brings you back to A. Okay. And then the third dot point is A, and then the operation B inverse brings you to B inverse operation A inverse. Okay. And finally, dot point 4, if A star B equals A star C, then B equals C. So this last dot point is really just like a cancellation law, right? So if you have, for example, I don't know, like A times B equals A times C, it just means that you can cancel A on both sides. Okay. All right. Now the next part to have a look at is fields. Fields builds onto groups a bit more. So with fields, you have that you're extending the idea of groups by adding on an additional operation. So remember with groups, you have a set G, and then you had the operation, for example, star on there, whatever star may be. Okay. Field just adds on an extra operation. So you still have some set, in this case F. So in this case F. But then rather than just having the operation star, you have two operations defined on it, right? So in this case, they notated it as plus and times. That's what it usually is, but just be aware that it doesn't always necessarily have to be the normal addition and normal multiplication. Okay. But so then basically for the first dot point, so basically in general, in order for something to be a field, you first require that the group with the set F and the first operation is abelian. So abelian, remember, is not only just a group, but it's also a group that commutes. And recall that this means that. So it also has to be a group where you can interchange the order of your elements when you perform operations on them, and it's still the same. Okay. And the second dot point is that you have the set F omitting the 0 element with under the operation, under the second operation, and that is also still abelian. So same thing as before, okay, except this time it's omitting the 0 element. Okay, so it has to be a group, and it also has to be a group that commutes. Okay, and finally, it has to satisfy the multiplicative multiplicative distribution laws. So for example, A times B plus C gives you A times B plus A times C. Okay, so it may seem like there is less to prove than a group, but because there's only 3 dot points here, but in reality, there's quite a lot more to prove than a group, because for each one of these first 2 dot points, you have to firstly prove that these things are abelian groups before we can proceed. Okay. The next idea we're going to have a look at is subgroups and subfields, now that we've gone through fields and groups. Okay. From first year, you would have dealt with subspaces. The idea here is fairly similar, because we only have to prove a portion of the properties for a group or a field to say that something is a subgroup or a subfield. So theorem 1, subgroup theorem, it says that consider a non-empty set A that is a subset of G, where G under the operation star is a group. Then the group A under the operation star is a subgroup if and only if all elements of A satisfy these 2 conditions. So remember, for groups, you need 4 conditions. To prove something is a subgroup, you only need 2. The first one is closure under the operation. So suppose A and B are elements within A, then A star B is still within A. So same thing as closure in the normal group definition. And similarly, existence of inverses. So again, same definition as the one in just the group definition, right? For any element A, its inverse must also be within A. Okay. Okay. So let's have a look at the first example. Consider B as an element within G, where G is a group under the operation, I'll just call it dot. Prove that H, being this set, B dot A dot B inverse, where A is an element within G, is a subgroup of G. Right? So all the elements within G that satisfies this condition here, that set is a subgroup of G. Okay, under the operation dot, of course. Okay. So the first thing, if you have a look at the previous slide to prove, is actually not this or this, but rather it's this. Right? So this is something you have to be careful of. This is always something you have to at least make a statement about to show that it's non-empty. before you go on to prove these other 2 dot points. Okay, let's have a look. We must firstly check that H is non-empty. And we can simply check whether or not the identity element E is in H. Okay, so this E here, to be more specific, is the identity element of G. Okay, we know that there must be this particular we know that there must be this element within G because every group has an identity element. Okay, so if we can prove that E is also within H, then it's non-empty. Okay, so if we choose A equals to E, right? Because remember, A is some element within G, so it's like absolutely fine for us to choose that A equals to E. And if we do so, then B dot E dot B inverse, well, since B is an element within G, well, B dot E, this part here, would just be B again, right? Because recall that the identity element E brings you back to what you just, I guess, performed the operation with, right? So remember, like A star E just brings back to A, right? So B dot E just brings you back to B. But then this gives you this line. But then B dot B inverse is just something operating with its inverse. So you just get back to E again. And E is within G, as we have previously stated. And so E is also at least within H. And so H is non-empty. Right? It at least contains the identity element from G. Okay. So that has shown that it's non-empty because it at least contains E from the bigger group G. Now we can move on to the other 2 dot points. The first dot point is closure. Consider X and Y being elements within H such that X equals to B dot A dot B inverse and Y equals to B dot C dot B inverse for some A and C within G. Again, just like how we proved something was a group in like the very first example, we said X and Y within this particular group, and we kind of just like in the first line stated what that means. So if X is within H, that means that X can be rewritten as B dot A dot B inverse for some A, and Y can be written as B dot C dot B inverse for some C. Right? We're really just using the definition of something being H here. Okay. And so if that's the case, then we have to just check that A dot Y is something that again ends back up within H, because that's what it means for it to be closed. If you take 2 elements within the group and then I guess put them next to each other with operation in between, you end up again with something in the end that is within the group you started with. Okay. So you have X dot Y. X is this, Y is this, and you have a dot. And you have a dot in between. And then by associativity of groups, we can rearrange the brackets. And so we do so, changing the brackets from here and here, here and here to here and here, most importantly. Because what that does is that gives us the identity. B inverse dot with B just gives us E again. But remember, then that doesn't really matter, because if you have B dot A dot E, that would just give us B dot A again. So B dot A dot E would just be B dot A again, right? Because if you times something, or if you dot something with the element, you just get the same thing back. Okay, so that gives us this next line here. But then again, if you again use associativity to rearrange your brackets, you can purposely rearrange it such that you have A dot C in the middle and you have B and B inverse on the ends. But what is this? This is exactly the definition of something being within H, right? The definition was you had B dot, say, some random element from G dot that. In this case, it's just that in particular, our, let's say Z is A dot C, right? And as A and C are already elements within G, and since G we know is a group, then A dot C must also be an element within the group, because G must have closure. If G we know is a group, it must have closure, and so A dot C must again be something within G, and so we have, just like we wanted, B dot something within G dot B inverse. And so we can claim that X dot Y is closed under the operation dot as well. Okay. Now the next property we have to prove is that its inverse exists and lies within H. Okay. For this particular example, we're going to claim something as its inverse and prove that it actually works. Okay. So we're going to claim that Z is B dot A inverse dot B inverse. So where did we get this from? Well, if you recall, something being within H must satisfy this. Oops, sorry. Yeah. In this particular example, we're just interchanging the A to become A inverse. And we're just hoping to show that X dot this thing here, or sorry, this thing here, will bring us back to the identity element E. Okay? And if it does so, then it will work, right? So the whole idea of this is just that we're going to replace the previous working out with A inverse. Yeah, the whole point of showing that A inverse works, okay, or that it exists within H, okay. And so if we set Z to be this and A inverse to be within G, and we know that A inverse is within G because if G is already told to us as being a group, then if A is an element within G, its inverse must also be within G. That's the fourth property of a group. Okay. So X dot Z will give us, I'll just write it out, give us B dot A dot B inverse dotted with B dot A inverse dot B inverse, right? And again, if you use associativity, we can interchange the brackets such that we have this bracket here, B inverse dot B, but then that just becomes the identity, so that disappears. But if you think about it, if that disappears, then now you're left with B dot A inverse dot B inverse, right, which is this line here. But A dot A inverse will be the identity. Say that disappears, and say you're left with just B dot B inverse. But B dot B inverse will just become the identity. So that disappears, and you're left with just E. And so therefore we have shown that for any A, if you choose this particular Z, it will work out, because in the end, no matter what your A is, you end up with E, which is the identity element. And so therefore we have proof that it's a subgroup. Right? So we only show we only show two examples there, right? So I mean two conditions. First condition, there's closure. Second condition, that its inverse exists and lies within the group H. Okay. Yep. So it's just saying what I finished off there. So a similar argument applies to Z dot X equals E, and so any element X or A or whatever from H also has an inverse. And so by the subgroup theorem, H is also a group on the dot. And annotation wise, we say that H is, I guess, less than or equal to G. This is the notation for subgroup. Okay, so HV is a subgroup of G under the operation dot. Okay. Now the next thing we'll have a look at is morphisms. Just like how we can define a mapping between any two sets, we can also define something similar between two groups. Okay. Consider two groups G and H. The mapping F from G to H is defined as a homomorphism from G to H if it satisfies the following property. F of A star B equals to F of A dot F of B. So what that is saying is, here you have F of and then two elements within G applying operation within the domain. And what I mean by that is G here, that's a domain, that's the codomain. If we apply the operation in its domain, A star B, it will spit back out F of A independently and F of B independently under the operation in the codomain. Okay. So remember, so I guess be careful here that this is the operation in the domain, and this is the operation in the codomain. and this has to be true for any A and B within G. Okay. And furthermore, if this mapping here is a bijection, which means that it's both surjective and injective, we can furthermore say that both groups are isomorphic to each other. Okay. Some properties of homomorphisms. The inverse always maps back to the inverse, and the identity always maps back to the identity. So f of A inverse gives you f inverse of A, and f of E equals to E dash, and the reason why there's a different notation here is that this E here is the E in G, and this E dash here is the E in H, right? Because recall, we're working over two different sets or groups now, and so the identity element for G may differ from the identity element for H, but it doesn't matter. Okay, so we're just saying that f of E gives you E dash, where E is the element from G and E dash is the element from H. Okay. So let's have a look at an example here. Suppose that G, that matrix there, is a group under matrix multiplication. Is G isomorphic to the real numbers R over addition? Okay. The first thing to prove before we can check whether it's isomorphic or not is to check whether it is even a homomorphism, right? Because remember, isomorphic is like an extra condition, kind of similar to how abelian is an extra condition on groups. Isomorphic is something that's extra on top of homomorphisms, right? If something is a homomorphism, then we can furthermore try to show it's isomorphic or not. Okay. Yep. So we firstly show that this is a homomorphism. If we take Fs and Ft, right? So Ft. Okay. So I guess we should define this properly first. We're going to define this matrix here as just being Ft. Just for the sake of easier notation, so we can interchange this value here. Okay. So we have Fs and Ft. So Fs will just be that same matrix before, but we replace every T with S, and Ft is just the same matrix as before. Okay. We were saying that in the domain it was under matrix multiplication, and so we take these two matrices and apply ordinary matrix multiplication, and if we check, it will become this, right? If we take this row times this column, this row times this column, this row times this column, and so on, you will end up with this matrix here. Now, from this matrix, we can tell that it is indeed actually equal to f of s plus t, right? Recall that that is what we wanted to show. We want to show that if we take f of s and f of t separately and take the operation in the codomain, it's the same as if you took f of the two elements and did the operation in the domain, right? That was the whole point of f of a star b equal to f of a dot f of b, right? That's what we're doing here. We have f of s and then the operation within the domain t equal to f of s operation in the codomain ft. Yeah. So why is this true? Why is this matrix here equal to this? Well, around the side here, this matrix here, f of s plus t, would be the same as if I replace all these s's here with s plus t instead. Like this, right? Again, it's just replacing all of these s's or these t's here with s plus t instead, right? And if you look carefully, these two things here are equal, right? Clearly, this is already obvious, right? And this particular element in the top right-hand corner is equal to this if you just expand this out, or if you just complete the square here. Right? If you factorize out a half, it will become t squared plus 2st plus s squared, which is the perfect square, s plus t bracket square. So that's what these two things here are the same. And so you have this. Okay. And so from this, we do see that G and the real numbers R is a homomorphism. Now the only thing we have to check is, well, is it also isomorphic, right? And just by looking at the definition of what they gave us, we can indeed see that it is a bijection as well, which means it's both injective and surjective. Okay, I'll briefly explain that. If we go back to this here, I guess in particular, this here, if we define this matrix as Ft, okay, then it's both injective and surjective, because surjective is saying that with everything in the codomain, there's at least something in the domain that you can choose to make it work, right? Well, let's say you're given any matrix of this form, right? T could be 1, could be 2, could be 3, could be -5, could be whatever it is. It doesn't matter, because that just means that in my codomain, I would have just selected the inside of this F here to be equal to whatever that was. Right? So for example, if this matrix here I'm given, and instead of T, it's 3, so 1, 3, 3 squared on 2, 0, 1, 3, 0, 0, 1, then I would have just selected T equals to 3. Right? So whatever is in this matrix, I would just select T equals to that. So it's at least surjective, right? But then on top of that, it's also injective, because there's a direct mapping from whatever I choose in here and whatever this element here is, right? If I chose, let's say, T equals -1, these two here must be -1, right? There's no way where I have a matrix and I can have, I guess, more than one possible mapping, right? So let me give one more example. Like for example, if I chose T equals -1, in here, this would have given us half, right? So perhaps you thought that, okay, back in Ft, I could have chosen +1 or -1, and it would work because here I have a square, right? But that's not the case, because there's a direct mapping between what's in my F and what's in these two positions. If I chose 1, these two would exactly be 1. If I chose -1, these would be -1, right? And so it would give us a different matrix depending on whether I chose 1 or -1. And so given whatever matrix you have in the codomain, there's at least, I mean, there's also at most one thing I can choose in the domain to make it work. And so since that's injective, then I have both injective and surjective. And so it's a bijection, and so it's isomorphic. Okay. Good. Okay. So that way, firstly, I've shown that it's a homomorphism, and secondly, that it's both injective and surjective, I guess just by reasoning here. And so it's also isomorphic. Okay. The next thing is kernel and image. Consider a homomorphism F from G to H. We define two special types of sets that come from this mapping, namely the kernel and the image. The kernel is the roots of F, so it can be thought as the roots of F. So basically, it's anything within the domain where if you take F of that thing, you get brought to the identity element of H, right? So it's saying if I take F of this element A, then it brings me to the identity of the codomain H. Okay. And the image is something that projects you to the codomain. So now it's a set of everything in the codomain where if you plug in any x from your domain G, then it gives you something from your codomain. Okay. So if you think about a kernel is something that is a I guess a subspace of your domain, and image is something that is a subspace of your codomain. Yeah, so kernel is anything within your domain where if you apply F to it, you get brought back to the identity of its codomain, and the image is any element within the codomain that came from something in the domain. It's basically the intuitive idea behind it. Okay. And this leads us on to have a look at vector spaces and vector subspaces below. So vector spaces is that you have quite a few properties you have to check, right? So you have that firstly, V under addition is an abelian group. Again, recall that abelian group firstly has to be abelian, has to be a group, and then secondly, it has to also commute for it to be abelian. And the next condition is that there must be scalar multiplication. So any scalar from the field F in this case is valid, right? So, like, it has to make sure that the field F you selected, scalar multiplication must work with it, okay? And then the third condition is that there must be associativity of scalar multiplication. So alpha and then bracket beta V is the same as alpha beta in brackets times by V, where V is the vector and alpha and beta are scalars. D, 1 times the vector V must be just V. E, alpha and then brackets U plus V, which are vectors, must expand out to be alpha U plus alpha V. So E and F are kind of like the distributive laws, right? And then F, you have alpha plus beta, which are scalars, times the vector U, must give you alpha U plus beta U, okay? So E and F you can just think of as being the distributive laws, yeah, okay? And then the other idea is vector subspaces, which just like subgroups and subfields, like we previously covered, there's a theorem you can use that significantly simplifies what you have to prove, okay? So if you want to prove something is a subspace, you need it to be a non-empty subset of, I guess, your biggest space here, for example, V. And then U would be a subspace of V if it follows this condition, which you can basically think of as being like a linearity condition, right? Because this is basically saying scalar multiplication of an element and addition works, yeah? If you have that it's non-empty and that this is satisfied, so basically closure of when you take a linear combination of your elements X and Y, then you can already claim it as a subspace, okay? Here's a brief explanation of why these are the only two conditions needed, okay? So let's have a look at an example. Consider the set W1, where you have this matrix here, where x1 and x2 are elements from the real numbers. Prove that W is a subspace of the 3x3 matrices with real entries. Okay, let's have a look. Clearly, W is a non-empty subset of the 3x3 matrices, okay? And I'll briefly explain that. If we come back to what W is, well, it's not empty because I can just select anything from the real numbers here, and I won't just get the zero matrix. For example, if I choose x1 equal to 1 and x2 equal to 0, then I would get the matrix 1, 0, 1, 3, correct? So at least this must be an element within W, and so W must be non-empty, right? So that was really easy. You just had to choose any number x1, x2, and it would work out, okay? And the next part is to prove that this linear combination of any two elements x and y from G and any lambda from the scalars is closed. Okay, it's closed under it's closed. So you have x would be the matrix x1, negative x2, x1 plus x2, 3x1 minus x2. And then lambda y would be plus lambda times the matrix where you just replace every x here with y. Okay, so y1, negative y2, and so on. Just under normal matrix addition, you would end up with the next line here. So from here to here, you just take this plus lambda times y1, and then this plus lambda times negative y2, and so on, right? And then once you have that, you realize that this matrix here is actually in the same form as what they told you as the definition of W, right? If you recall what that was just this. right? Something within the set W1 had this sort of matrix, right? I'll just replace these x's with u's, for example. It had to be something in this form, right? If it was an element within the set W, right? And if you look at this big matrix here, that's exactly what we have. The only difference is that we have, instead of U1, we have x1 plus lambda y1. And instead of U2, we have x2 plus lambda y2, right? So U1 and then negative U2, so negative x2 plus lambda y2. And then U1 plus U2, we have x1 plus lambda y1 plus x2 plus lambda y2. And in our fourth element here, we have 3U1 minus U2. We have 3x1 plus lambda y1 minus x2 plus lambda y2, right? And so we do have a matrix in the same form as W, just that it looks a bit more complicated, but it's still the same thing. And so then we can claim that x plus lambda y is also an element within the group, or like within the space W here, or within the set W here, okay? And so we have proved that linear combination of any two elements within G is still closed under W. And so by the subspace theorem, we have shown that W is a subspace of the 2x2 matrices with real entries. So I think this should actually here be W, X, and Y being elements within W1. Okay. Again, this is the same notation as what you saw for subgroups, I believe. So it's still this less than or equal sign. Okay. Okay. Next thing to have a look at is span. So suppose we have a set of vectors S, V1 to Vn. We define the span of W as a set of all possible linear combinations of the elements of W. The span of S is, if we take lambda 1, lambda 2, lambda 3, all the way to lambda n, where these lambdas are all scalars. They don't have to be the same scalar. They could be different. They could be the same. It doesn't matter. But you take all these scalars and times it by, for example, lambda 1 times V1 plus lambda 2 times V2, all the way to lambda n times Vn for any one of these lambdas, and you get the entire span of S, right? So it's basically all possible linear combinations of these vectors V1 to Vn. It is quite easy to see that span of S is a subspace of V. And in the case where span of S is equal to V, we call S a spanning set. So that's saying if these vectors V1 to Vn, if we take any linear combination of that and it covers your entire vector space V, then S is called a spanning set. It spans the entirety of V. Okay. The next idea that's closely related is linear independence and dependence. We say that a set is linearly independent if only the trivial linear combination matches a zero vector. So what that is saying is, if we take a linear combination of all the vectors in that set, so V1 to Vn, and set it equal to 0, it's linearly independent if the only way this is true is if lambda 1 equals to lambda 2 equals to lambda 3, blah, 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 all the way to equal lambda n is equal to 0, right? So it's only linearly independent if all these lambdas equal to 0, okay? And if this is not true, we call the set linearly dependent, okay? Okay. Show that this set B here, cos cube t, cos squared t sine t, cos t sine squared t, and sine cube t is linearly independent. Okay. So let's have a look. The first thing we have to show is that if we set a linear combination of these elements equal to 0, we have to show that lambda 1 in this case has equal to lambda 2 equal to lambda 3 equal to lambda 4 equal to 0. If that is true, then it is linearly independent. Okay. So yeah, so like I said, we are intending to show that every lambda here is equal to 0. To do this, we use a little trick here, and we use the fact that, okay, this line here has to be true for any value of t, right? So if if this has to be true for any value of t, then I can just plug specific values of t in to try force my way out and say that lambda 1 equals 0, lambda 2 equals 0, lambda 3 equals 0, and lambda 4 equals 0. So the first value we're going to sub in is t equal to 0. And why we do this is because if you think about it, if I plug t equals 0 into this left-hand side here, all these terms here will disappear because sine of 0 is 0. Right? Sine of 0 is 0. And the only term left would be this first term here, because cos of t is 1. Right? That's why I have in the end here lambda 1. But this whole expression here is equal to 0. And so lambda 1 equals to 0. Right? So just by subbing in t equals 0, I've shown that lambda 1 is equal to 0. And this is okay because, like I said, this equation here has to be true for all values of t. So there's nothing wrong with me particularly choosing to sub in t equals 0. Okay. Now we'll use the same method to show that lambda 4 is equal to 0. But instead of plugging in t equals 0, we're plugging in t equals to pi and 2. The reason why I choose this is because cos of pi and 2 will be 0. So this will disappear, and this will disappear. And so you'll just be left with lambda 4. But again, we're trying to look at this entire expression equal to 0. And so lambda 4 equal to 0. And so we have lambda 1 and lambda 4 both equal to 0 now. Now that we have lambda 1 and lambda 4 equal to 0, that greatly simplifies our equation. We don't have this first and last term anymore. We just have lambda 2 cos squared t sine t and lambda 3 cos t sine squared t. Now we can also ultimately show that lambda 2 and lambda 3 are both equal to 0 just by subbing in pi equals 4 and negative pi on 4. All right, I'll briefly go through that. If you plug in pi and 4, well, you would get lambda 2. Cos squared would be half, because cos pi and 4 is 1 on root 2. And sine pi and 4 would be 1 on root 2. Then you plus lambda 3, 1 on root 2, half. All right? And that would be equal to 0. Okay? And if you plugged in negative pi and 4, you'd have just the slight opposite of this. You would have that plus lambda 3, 1 on root 2, half. Right? So as you notice, the only difference here is this term here. That's positive, that's negative. This term on the end here stays the same because cos is positive in the first and in the second and in the fourth quadrant, right? And hopefully from this you can see that when you do your simultaneous equations, you would end up with lambda 3 equal to 0 and lambda 2 equal to 0. Because for example, if you add these two equations, these two terms here will cancel. Then you have lambda 3 times something equals 0, so lambda 3 must be 0. And then if lambda 3 is 0, lambda 2 must be 0. Okay? And so the set B is linearly independent. Okay, because all the lambdas equal to 0. The next thing to have a look at is basis. Naturally, when we look at spanning sets, right, we want to look for the minimal spanning set. Okay? And the way we define this is it must follow two properties. Firstly, that this set S spans the entirety of the vector space you're looking at. And secondly, every element in this S is linearly independent. Okay? Why these two properties only? Well, the first one is obvious because we want to span the entire set. That's why we want to span S equal to the entire vector space. And secondly, by having linear independence, we are saying that every vector is important in that span, right? Because if it was not linearly independent, then some vector, so let's say some vector vk, for example, could be written as a linear combination of all of the other vectors within that set. But then that means vk is kind of redundant, right? Like we never really needed vk then. Yeah. So by having linear independence, every vector has importance in that set. And so I guess that's why they say it's similar to saying that they pull their own weight. Okay. Some notable qualities of a basis set: uniqueness of representation. So this will be covered kind of when we talk about corner vectors. and it's dependent on the type of field. The easiest basis that we can think of are the standard bases. So for example, Rn, a vector of n dimensions. You have E1 all the way to En, where for example, E1 is just 1, 0, 0, 0, blah, blah, blah. And say E2 is 0, 1, 0, blah, 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 0. It's just having a 1 in whatever this position it is notated at. Okay. The n by n matrices, similar concept. E11 would just be this matrix here. Right. It would just be having the entry 1 in this position, the 1, 1 position. Second matrix would be the same thing, but having the 1 in the 1, 2 position. Okay, and so on. Dimensions. So not only are there multiple bases for each vectors, but they all have the same number of elements. As a result, we define the following useful concept of the dimension of a vector space. Consider a vector space phi, which has finite spanning set S. Then we define the size of S to be the dimension of V. So if you have, basically if S is a basis, so that means it is spanning and it's linearly independent, like every element within it, then the order or the size of S is a dimension of V, right? So we're saying here that any one of these spanning sets or any of these bases, to be more specific, all have the same number of elements, and so the dimension of that vector space can be expressed as that same number of elements. Yeah, so whatever that size of elements there are, that's what we call the dimension. Okay. So this leads us to a lemma for equivalent ways to prove something is a basis. Firstly, S is a basis of V. It's the same as S is linearly independent, and also the size of S is equal to the dimension of V. All right, so here. Or otherwise, S is a spanning set, and the size of S is equal to the dimension of V. Usually the one we use is the second one, because linearly independence is usually easier to prove than it's a spanning set. And also this condition here is usually pretty easy to see as well. You can usually just count the number of elements in the S they give you, and also go back and check, okay, well, what was your vector space? For example, if it was the 3 by 2 matrices, then it would be dimension 6, and so on, right? So you can just check if these two numbers here are equal. If they are, and you have also proved that there's linearly independence, then you're done. Okay. So let's have a look at an example here. Consider the degree 2 polynomial vector space P2R. Show that the following set is a basis of this vector space. Firstly, we note that S is composed of 3 elements, and that P2R is also a vector space of dimension 3, right? Because P2R would be any polynomial that looks like this. Okay, and so you have 3 phi parameters here, A, B, and C. Okay, so P2R is of dimension 3, and that's equal to the size of S. There's 3 elements here, and so we have already satisfied one condition, that the size of S is equal to the dimension of the vector space. We only have to now show that it's linearly independent, and then we're done. So we set up the usual linear independence equation. Lambda 1 times the first element plus lambda 2 times the second element plus lambda 3 times the third element equal to 0. And we just have to show that lambda 1 equals lambda 2 equals lambda 3 equals 0. We group up all the constants, all the x terms and all the x squared terms, set it equal to 0, and then we form a matrix. Okay. So if you compare the coefficients on both sides, you would have that 2 lambda 1 plus lambda 3 equals to 0, because on this side we can think of it as being this. So we compare this to this, this to this, and this to this. Then that would give us the matrix on the other slide. We have 2 in the first slot, 1 on the far right, and then 3 in the first slot, 4 in the middle slot, and then -1 in the middle slot, 1 on the far slot, right? That gives us this matrix. We then reduce it, and we get that. And then clearly, since every single column here is a leading column, our set is linearly independent, and so we're done. Okay. The next thing we have a look at is coordinates. So I briefly talked about this already before. It's basically the idea that we can uniquely express the linear combination, right? So if you have a basis B composed of vectors V and some x within the vector space V, then when you write x as a linear combination of all these vectors V, all these scalars, like all these alphas in the front, all these coefficients here, can be composed together to create a vector like this. And we call this vector here a coordinate vector. And what we said before was that these vectors here, given a certain basis, is always unique. There's only one particular way that you can have these scalars out in the front. Okay. So how do we find them? The most basic approach is to find them by solving the matrix equation V times alpha equal to x, where V are the column, where the columns of V are the basis vectors. Okay. So let's have a look at an example. Let V be the vector space of all 2 by 2 real symmetric matrices. Will we be able to access these slides? I think they should be uploaded a few days after the lecture or the seminar. Yeah. Okay. So going back to the question, all 2 by 2 real symmetric matrices, and we have A equal to 9, 5, 5, -4. Find the corresponding coordinate vectors with respect to the following basis. Firstly, as an aside, you realize here that this basis B only has 3 elements in it. It has 3 matrices. Usually, 2 by 2 matrices have 4 elements, and so you might expect that there is 4 matrices in this basis. But recall that we're working over the real symmetric matrices, which means that every matrix has to be of this form, right? Where this diagonal here contains the same element. And so that's why our basis only requires 3 elements, right? Because the standard basis, if you think about it, would just be this. Yeah, because this matrix here already covers 2 of the entries. Okay. So we have to find the corresponding coordinate vector for A with respect to this basis here. Let's see how we're going to do that. We want to find the scalars alpha, such that when we take alpha times the first element in that basis plus the second element in that basis plus the third element in the basis, these alphas will form a unique coordinate vector, right? So in a sense, what we're doing here is we're taking the first element or the first entry of each matrix, 1, 2, 4, and we're augmenting that against 9. Because if you think about it, if we have alpha 1, alpha 2, and alpha 3 times by these 3 matrices has to equal to A, then we have alpha 1 times 1 plus alpha 2 times 2 plus alpha 3 times 4 equals to 9. And then we would have alpha 1 times -2 plus alpha 2 times 1 plus alpha 3 times -1 equals to 5, and so on, right? So we have the scale, or like the linear combination of each single entry equal to each single entry within A. And so that's where we form our matrix here, right? 1, 2, 4, 9, -2, 1, -1, 5, and 1, 3, -5, -4. We then proceed to reduce this, okay? And we get this in the end, and then we can just back sub, right? So by back substitution, you can have alpha 3 equals to 88 on 52, which is 22 on 13, and then you back sub that into this row. Once you find alpha 2, you back sub into this row, you have alpha 1. And so the coordinate vector of A with respect to B can be written as, if I just take the 1 and 13 out, alpha 1 first, so -29, alpha 2, 29, alpha 3, 22. Okay. Now the last part of this of this section is having a look at sum of vector spaces, which is part of MATH2601 only. Suppose we have two subspaces U and W within V. We define their sum as being the set of all vectors in the vector space V, where Y equals to some vector U plus some vector W, where U is some vector in capital U and W is some vector in capital W. And furthermore, if the intersection of capital U and capital W is only the zero vector, or in other words, is trivial, then we have a direct sum. And we denote that by U and this circle addition W. Okay. We also have another theorem here that talks about dimensions. If you have dimension of U plus dimension of W, you get dimension of U plus W plus the dimension of U and W. For any of you that have done probability or whatnot, there is a very similar, I guess, formula to this, which is A union B equal to BA plus BPB, and then minus P of A and B. Right? It's very similar to this. This is just probability. This is dimensions. Okay. So let's have a look at our last example for my part in this seminar. The sum of subspaces example. If we have the subspace S and the subspace T, so S is all matrices A that are 2 by 3 matrices over the complex space. If you have A times the vector 1, 2, minus 1 equal to 0 vector, and basically S is the set of all A's that satisfy that condition, and T is a set of all A's that satisfy the condition that the row vector 1, 2 times the matrix A gives you the zero row vector. Part I asks you to find a basis for S and T, S and T. Sorry, S intersection T, S and T. Okay. Let's start off by defining A as being some 2 by 3 matrix, so A, B, C, D, E, F. Then for S, we would have that the matrix A times the vector 1, 2, minus 1 equals to this next line here, which is just your normal matrix times vector. And recall that in order for A to be within S, this has to equal to 0, 0. Then if you compare each row here, you would end up getting C equals A plus 2B and F equals D plus 2E. And that means that any matrix that's in the set S can be rewritten as this form here. A, B, D, E are free parameters, but then your C and F is fixed. Once you've chosen an A and B, your C has to be A plus 2B, and once you've chosen a D and E, your F has to be D plus 2E, and that's where you get this matrix from. And so clearly you can just cook up a basis from this, right? You'll just get this because you have your A's in this entry and this entry. For example, if you go back, you have an A here and an A here. And then, for example, you have a B here and 2 B's here. And so that'll give you your 0, 1, 2, 0, 0, 0, and so on. Okay. Similarly, if you apply the same logic to T, you would end up with the restrictions A plus 2D equals 0, B plus 2E equals 0, and C plus 2F equals 0. And so once you fix D, E, and F, then your A, B, and C are also fixed. You have no more choice once you've chosen your D, E, and F. And so you get these three matrices here. Negative 2, 0, 0, 1, 0, 0. That comes from this first restriction because A has to equal to negative 2D. So once you choose D, your A has to be negative 2 times that. And the same logic applies to these other two. Okay. Oops, I think this should be a 0. Okay. Now finally, for S intersection T, there's a short method here. We observe that this will require all 6 restrictions shared amongst S and T, because in order for something to be within S intersection T, it has to be within S and within T. So it must have all of these restrictions. So this and this, okay? Oops. So looking at the restrictions on S, we saw that once we chose A, B, D, and E, C and F had to become fixed. And when we looked at the restrictions on T, we saw that once we chose, let's say D, E, and F, then A, B, and C had to be fixed. But from part B, we already know that these two have to be fixed, right? We already know that C and F have to be fixed. It's only between these four, A, D, B, and E. And so if we choose, let's say, D and E, then A and B has to be fixed. So in the end, no matter how you try to, I guess, fix your entries, S intersection T will always only have 2 free parameters, right? Once you choose 2 of your entries, then everything else must become fixed. And so we have S intersection T is of dimension 2, as 4 of the 6 entries will become fixed when you choose any 2 of them. So rather than calculating S intersection T, we'll just try to cook up something, or we'll just try to cook up 2 matrices that will make it work. If you go back to the previous slides, you would realize that -2 times the first matrix added to the third matrix of the basis for B, for the basis of S, is equal to the first element added to the third element of the basis of T. I'll just go through this very first one, and I'll leave the second one for you guys to check, because we're kind of running low on time here. So going back, we're looking at -2 of the first plus the third equals to first plus the third of T. So let's go back and have a look. Whoops, did I do? Okay. You go back here. -2 lots of this one plus one lot of this one would become -2, 0, -2, 1, 0, 1, which is the same as if you took this one and added it with this one. Then you get -2, 0, -2, 1, 0, 1. And so just by observing the bases for S and T, we have found a particular linear combination of the elements within the basis that intersects, right? These 2 matrices here are equal. And so we can just choose this to be one of the basis matrix for S intersection T, okay? And then all we had to do was then observe at least one other one, because once we did, we would have 2 different matrices. And so since we know that the dimension of S intersection T is 2, these 2 is good enough, right? And finally, part double I. So does S plus T equal to the vector space V give a reason? Well, if we use the theorem on the dimensions of the sum of subspaces, then it wouldn't work, because we have that the dimension of S plus T is equal to the dimension of S individually plus the dimension of T individually minus the dimension of S intersection T. That gives you 5. But recall that V was all of the 2x3 matrices, and so the dimension of V is 6. And so since the dimension of S plus T is not equal to the dimension of V, S plus T does not even span V. Okay, and so that's why S plus T does not equal to V. Okay, that concludes my portion of this first seminar. Bruce will be coming in to teach the second half of this first seminar, so I will hand it over to him now. So thanks everyone for coming for now, and just wait a second and Bruce will hop on to do the second part of this first seminar. Okay.
Alright, it looks like that's working. Maybe I'll just wait for a confirmation. Yep, cool, thanks. Alright, so what we'll do, thanks Jay, for going through that first section, we'll be going through linear transformations and inner products. Alright, so we'll start off with linear transformations. So Jay talked about homomorphisms between groups, which are basically maps between groups. So we're going to do much the same thing. We're going to talk about maps between vector spaces. So we have a vector space V, a vector space W, and both of them are over the same field F. Alright, and what we have to be able to do is find a transformation such that when we take t of x plus y, we can really just take them separately. So take t of x plus t of y. So that's basically functionally equivalent to saying we can just take this plus sign out. Right, this plus sign can just be taken out of the t. Right, same thing with scalar multiplication. We have t of a lambda times x. We can really just take the lambda out as well. Right, so we might have looked at this in first year when we can basically take all this stuff out. So these two main properties, scalar multiplication and addition, and we can take them out. And that's what we'll do with linear transformations. The good thing is we don't have to prove both of these properties separately. We can combine them into a single statement. So if we have t of x plus lambda y, there's addition in there, and there's also scalar multiplication in there. So if we can prove that this expression is equal to just taking everything out of the t, so this thing over here, taking everything out, we've taken the lambda out, we've taken the plus sign out, then we can prove that it's linear as well. And that's what we're going to do over here. So just one simple example of a linear transformation. It's a transformation from the polynomial space P2R to R3. Right? And what it does is it takes the polynomial and it evaluates it at 1, so it takes the value P1, then P3, then P prime 2. Right, so how can we prove that this is linear? Well, what we'll do is we'll prove this thing again. So t of, in this case we might not use x and y, because we just have to take two elements from the vector space. In this case we have to show that t of p plus lambda q, where both of these are just polynomials in P2R. Right, we have to show that is equal to t of p plus lambda t of q. So the natural first step is just to evaluate this thing and see if we can just reduce this to this thing over here. So let's try that. So we've done this over here. We've taken two arbitrary elements of P2R, and we've taken a random scalar, so lambda is a real number, right? And we want to show that t of p plus lambda q equals, well, basically the other expression we had. So we'll start off by evaluating this. So t of p plus q, p plus lambda q equals p plus lambda q evaluated at 1. Then we have p of lambda q evaluated at 3. Then the same thing at 2. So the idea is we know from our function rules of addition that p of lambda q of 1, well, by definition, that's just going to be expanding everything out. So we're just going to be equal to this. It will just be equal to p of 1 plus lambda q of 1. And that's just because that's how we define function addition. Right? If we have two functions and we want to evaluate them at 1, we just evaluate them separately. So that's just going to happen over there. Same thing over here. This one looks a bit tougher because there's a differentiation sign. But we know that when we have the addition of two functions and we differentiate them, then we can just differentiate them separately and add them together. That's a property we know from first year even. So that means that we can just expand that out too. So once we've expanded it out, we get this over here. It's looking pretty nice. And the idea is we want to show it's equal to t of p plus lambda t of q. So what that means is we want to separate the p's and the q's, and we want to take the lambdas out. And that's what we do over here. We just rearrange this vector addition. We have p of 1, p3, p prime 2, and then we take away the q's. We separate this into the sum of two vectors, right? So we have p of q plus lambda q. We say we don't want to have these in the same vector. Let's just take away this lambda q of 1, and then we'll put it over there. Right, and it turns out that when we do this, we see that we get p of 1, p of 3, p prime 2, which is just t of p. Same thing with q, we just get lambda t of q. So all we have to do really is just separate the p's and the q's and see if it reduces down to that. And by that property, we've got it's a linear transformation by what's called our linearity test lemma. Cool. And so that's how we do linear transformations. So once we have a linear transformation T, Jay talked about kernels and images, and it turns out all of that applies to T as well. So the kernel is a set of roots of T, so basically a set of all elements in this codomain. So V, sets of all V in the codomain, such that when you map it, it just goes to 0, right? So that's basically a set of all roots as well. And the image, just like Jay talked about, is a set of all possible values that p of x can take, right? So let's just think about that for a second. So basically it's equal to the set of all values that we can get by chucking something into this transformation, right? So for example, if our map is just the 0 map, it maps everything to 0. So T maps all things to 0. Then what that means is that the image is just going to be the trivial subspace. Right, so if we do have something like that, the image is pretty simple, but generally the image is just kind of like the range of the function. And it can be proven that both of these sets, so both the kernel and the image, they're both going to be vector spaces. So specifically, because remember the kernel is a set of all vectors in V that map to 0, this is going to be a subspace of V. Right, so the kernel is going to be a subspace of V. The image is going to be the set of all values you can get in the codomain, right? So that's going to be a subspace of W, right? And that's going to be a really useful property. So when we talk about the kernel and the image, we like to talk about the dimensions of the kernel and the image, and they're called the nullity and the rank respectively. So the dimension of the kernel is just called the nullity, and the dimension of the image is called the rank. And we have this nice property that if we add the dimensions of these two things together, so if we add the rank of T to the nullity of T, we just get the dimension of this subspace, right? So the dimension of the domain, right? And this kind of makes sense, right? Because when we, if we have a lot of vectors mapping to 0, so remember the nullity is the dimension of the kernel. So if this thing is really high, then what it means is that a bunch of our vectors in V are all mapping to 0. Right, so there aren't many vectors left to map to other numbers, which is why our rank will be quite small. Because the nullity increases. Right, let's just write this out. Nullity increases. And it means our rank will decrease because we have a ton of vectors mapping to 0. So not many vectors left to map to other things, which is why our image has a small dimension. And we have these other properties. So if we have two vector spaces with the same dimension, then the following statements are equivalent. So if our nullity is 0, then, well, we can guess from the rank nullity theorem that the rank is going to be n. So it's going to be the entire thing. So in other words, if nullity is 0, then basically we can cover all of W. Right? So the dimension of our image is just going to be n, which means it's going to cover all of W. And if that sounds familiar, it's because that's a property of surjectivity, right? It means that we can basically cover the entire codomain, right? And long story short, if we can simply prove this property, then we know that T is going to be invertible, right? Because it means that it's going to be one-to-one between these two vector spaces, and it's also going to be surjective, so the entirety of W is covered. Right, so if we want to prove that a linear transformation is invertible, all we really have to do is find the nullity, right? As long as the dimensions are right. So as long as the dimensions are equal. So dim V equals dim W equals n. So we'll do an example of just rank and nullity, which is a bit from first year. Well, to make this a bit simpler, we have a linear transformation between R5 and R4, and we know that whenever we map between two vectors, so Rm and Rm, we can just express it as matrix multiplication as long as it's a transformation. And the process of doing that is what we do is we just take the coefficients of each one. So x1 has coefficient 1, so we say, okay, our first one will just be 1 over here. Right, then we just take the next one, this will be 1, 2, and we'll get 1 there. This will be 2, 2. Sorry, no, that wouldn't be 2, because we need an x3 as well. Right, so we take the coefficients from x1, x2, x3, x4, x5. This one will be 0, this one will be 2, this one will be 1. And the reason why this works is because if we take a and we multiply it by x, then we remember from our matrix multiplication, all we really do is we just go down the line, go down from 1, and then we multiply that by that one. Then the next thing we do is we take this one, we multiply it by that one too. Then we take 0, we multiply by x3. So in other words, the first element is just going to be all of these numbers multiplied component by component with these things. So what that means is that we will get this, basically. Right? So t of x will just be equal to this matrix times x. And we've basically completed the matrix on the next page. So tx equals ax, basically where this just represents the coefficients of each one. So 1 goes down there to 1, 1 goes down there to 1, 2. We just did that. And we also have over here, because there's no coefficients of x1 and x2, that'll just be 0. Then x3 has a coefficient of -1. x4 has a coefficient of -2, and so on. Right, so then we just represent this as matrix multiplication. And from then we can use what we used in first year to find the kernels and images. So what we can just do is row reduce, and we'll end up with something like this. We'll end up with a bunch of leading columns. So we can look at the leading columns. And we also have non-leading columns. And so when we did row reduction a bit earlier with linear independence, we recognize that these non-leading columns are basically, well, it was expressed as not pulling their own weight, right? We don't really need them. So these are not going to be necessary. If we want a basis for the image. And so what they want us to do over here is to find a basis for the image as well as the rank and nullity. So we know that over here, we'll take the leading columns, and they will correspond to the rank or the image. And these non-leading columns, they're not going to be necessary. They're just like our nullity. They just map to 0. Right? So specifically, what we'll do to find the basis of the image is we'll look at these leading columns, and we'll say, we'll just pick the first, third, and fourth. But we want to look at the original matrix. So instead of just taking the first, third, and fourth of this last row reduction, what we do is we just take column number 1, column number 3, column number 4 of our original matrix. So we get this. Rank equals 3, because it has 3 leading columns, and nullity will just be the remaining one. So nullity will be the non-leading columns, which is why our nullity equals 2. So rank equals 3, nullity equals 2. And then to find the basis of the image, what we do is we just select the columns in the original matrix that correspond to the leading columns. So what we just did, we got 1, 0, minus 1, and 1. And now we have, over here as well, we have 1, 0, minus 1, and 1. And we'll have 3 as well, because we had 3 leading columns. If we were to find a basis for the kernel, just be wary that you wouldn't be picking these ones. You wouldn't be picking these ones. What you would do instead is try to solve this system of linear equations, right? And you would use your free parameters. But we won't be talking about that. If there's confusion about that, you can ask about that in the chat. But we'll just be moving on from rank and nullity. Basically, the idea is to find a basis for the image. We just select the columns in the original matrix that correspond to our eventual leading column. So we get these 3 vectors. We'll move on to matrix representation of linear maps. So every linear map can actually be represented by matrix multiplication as long as both vector spaces, so T of from B to W, as long as both of these are finite dimensional. Right? So the idea is that before we had the property that if we have a linear map from Rn to Rm, we can express it as matrix multiplication. So we just did that kind of. The idea is that it's very much the same with any vector space. So if you have a polynomial space, right, so you want to do the differentiation map. So the map that maps a polynomial to its derivative. So this is just mapping the degree 2 polynomials to the degree 1 polynomials. If we have a map like that, for example, we'll map something like t squared to 2t. Right? It doesn't seem like that can be expressed as matrix multiplication because we've got a polynomial, and we can't exactly multiply polynomials by matrices, right? So what we have to do instead first is we have to find bases in each domain, and in the codomain of the domain. So what we do is we say, we can do this. We can say for the differentiation map, let's just continue with that actually. We start with a matrix like this, so t squared plus 1. That maps to 2t. Well, instead of trying to express this as matrix multiplication, we'll find a basis in the domain, so a basis in the domain. We'll call that b, and we'll find the coordinate vector with respect to that. So for the sake of an example, let's use the standard basis. So we'll take the coefficients, so 1, then we have 0, then we have 1. And this one will map to, well, the same thing, basically. We'll map to 0, 2. Well, now we do have vectors. We've taken a basis in each space, taken a basis b in the domain, and a basis c in the codomain. And now we do have two regular vectors. We have 1, 0, 1, and we have 0, 2. So now what we can do is we can actually find a matrix that maps between these things. So we'll say this one will be equal to some matrix A times this thing over here. Right, so the idea is that if we utilize our bases, so our basis B in the domain and basis C in the codomain, we can find a unique matrix representation. So we can find any matrix representation A such that if you take the coordinate vector of V with respect to the basis B and you multiply it by the matrix A, then that's just going to be equal to the result with respect to the basis C. So that's what this long formula means. It just means that we can map coordinate vectors from the domain to the codomain. And this is really useful because it means that we can find a really easy way to determine T of V. Right? So if we know the coordinate vector of V with respect to the given basis B, we can just multiply A by it and we'll get T of V with respect to C. Right? And so what we do, this is a really important notation. We write A equals T with a C down at the bottom and with a B down at the top. Right? So it's really important that C is the basis in the codomain and B is the basis in the domain. And if you write this out, it actually becomes somewhat a bit easier to remember. So T of V with respect to basis C equals T, and then you have a B at the top, C at the top, T at the bottom, and we have B of B. The idea is that we cancel out, right? What we do is we say this matrix is taking something with respect to the basis B, and it's basically converting it down to C, because this thing at the bottom, it tells us what the coordinate vector is with respect to. So this notation basically means B is in the domain, so it's taking a coordinate vector with respect to B, and we're converting it to 1 with respect to C over there. Right, so that's one way to remember it. You can also think of it as just cancelling out. So we're cancelling out down there. Right, so an important thing is that when we do this notation, we always cancel down like that. We never want to cancel up. That won't work. Right, so we'll always cancel down like this. Right, and so that's how we the importance of this matrix representation. How do we find it? Well, what we do is we say, let's take the basis B in the codomain, and the basis C in the codomain. Right, and we have to make sure we have a good order for them, so they'll be ordered bases. What we'll do is we'll say, let's let this one be B1 down to VP. So the basis for V will be equal to this, and that means its dimension will be equal to V. Well, what we'll do is we have a simple algorithm. what we do is we calculate T of V. Right, so we calculate T of V, and then what we do is we find the coordinate vector with respect to C. So J took us through doing that. All we have to do is solve equations, and then we calculate T of V1 with respect to C. Right, that's good. And we'll get a coordinate vector like this, something like 1, 2, 3, 4. That's a good vector. We'll make that the first column of our matrix. Next thing we'll do is we'll do the exact same thing with T of V2. Right, and we'll calculate its coordinate vector. Maybe we'll get something like this. We make that the second column. And you guessed it, you do that all the way down to VP. And maybe we'll get something like that. But the idea is that all we do is we go through our basis vectors, we calculate T of V1, and we take it with respect to basis C. Then we do the same thing for all the rest of them. Right, so that's the procedure. And the trick is over here when we have this thing. So coordinate vectors, finding them is quite an involved task. So because it's such an involved task, we'd prefer not to do it sometimes, especially if B and C are not standard bases. So when B and C are standard bases, then this will be quite easy, because it's just going to be, well, when we take a polynomial with respect to the standard basis, that's just going to be 1, 1, 1, and it's pretty simple. But when we don't have standard bases, we don't want to do this. We don't want to constantly have to do T of V1 with respect to C. We want to do the indirect approach. So before we can talk about doing that, we have to understand a few concepts first. So first of all, when we represent a linear map, we always do something like this. Yep, we'll do something like this. And we'll get this. Right, so we can use this to convert a coordinate vector in basis B to its corresponding function values, the T of V, in another basis. Well, the idea is that if we just do this with the identity map, which is just the map that maps everything to itself, then we can use this concept to convert from one basis to another. And that's the idea we'll be using when we have annoying bases. To get rid of them, we might try to convert them to nice bases. But this is called the change of basis matrix. Next thing, if we want to do two linear transformations on a vector, so we talked about function composition. The idea is if we want to do T composed with S of V, well, that's just the same thing as doing S of V first, then doing T of V to that result. So it kind of makes sense that if we want to do that, then all we have to do is take the corresponding matrix representations. So what we do is we say, let's do this function transformation first. S with A, B, and then V of, will be A. Right, what we do is we just take that, and that will be equal to S of V with respect to basis B. Then what we do is we take this other thing, so this thing on the edge, and we apply that over here. And then what we get is we get, well, basically the result of that. Right, so if we want to apply two functions, if we want to apply a function composition, we just multiply them together in the right order. Right, so that's what this is. And so a corollary of this is that if we've done a transformation, we've multiplied V by T, we've taken T, B, C, multiplied it by V of B, and we decide we want to go back, so we want to do the inverse of T, then all we have to do is multiply by the inverse of that matrix. So over here we have the property that the matrix representation of the inverse of T times the matrix representation of T will be equal to I, which means that these things are inverses. So if you've done a matrix transformation and you want to reverse it, just take the inverse basically. And that means that if we've converted a matrix from basis B to C, and we want to convert it back, all you have to do is multiply it by the inverse. So these two identity maps, you multiply them together, you get I, which means they're inverses. Sorry, that's not very clear. You get inverses. So that's what we're going to use when we're doing annoying bases. So let's think what we're trying to do here. We have a linear transformation that converts P to R to R3, and it has a pretty simple form. But the issue is they want us to do it with respect to some annoying bases, and they often want us to do that. So when we think about it, what we're going to want to do is find a matrix that converts any polynomial with respect to basis. So what's the basis of the domain? It's B. Right, then we multiply it by t with b at the top and c at the bottom. Then we'll get t of p with respect to basis c. Right, so again, if we're a bit confused about this, if we forget about it, just remember we're cancelling it down like that. Right, so this matrix is what we're after. We're after a matrix that takes a vector in basis b, then takes its linear map, then takes that answer with respect to the basis c. So those are the kind of steps we're after. So what the idea is we want to break it up instead. So what we might be asked to do with the direct method is we'll calculate we'll go down our basis in the domain. We'll do t of 1 plus t, and we'll take it with respect to basis c. Right, then we'll do t of 2 minus t squared with respect to basis c, and so on. Right, we'd rather not do that because it's a bit annoying to take basis vectors. So what we'll do instead is we'll just try to break it up into steps. So let's just explain what this means. So we start with a vector in basis b, right, because that's the domain. We don't want it to be in b because it's a bit annoying, so we convert it to s. So this is the identity map that converts the basis from b to the standard basis of p to r, to the standard basis of our domain. Now that we've got that, what we can do is just do our matrix representation with respect to the standard basis. And this won't be hard to calculate. And the reason for that is because when we go about our steps, so we take the basis v1, v3, and we take v of 1 and we find it with coordinate vector c, then c will just be the standard basis, which means its coordinate vector won't be too hard to calculate. So we always want to do our matrix representations with respect to the standard basis. So then we'll have this TSS. That'll be the matrix representation with respect to the standard basis. So now we've taken a vector in the standard basis. We've applied its matrix representation with respect to the standard basis. So now we're in the standard basis of the codomain. So the last step, convert back to the basis that they want. Right, so just a bit of an overview. We take a vector with basis b, we convert it to a nice basis that we like, to the standard basis. Then we do the standard matrix representation. Right, then we're in the standard basis again, but the standard basis in the codomain. So what we do then is we convert it back. Right, so now we can talk about how to actually calculate these components. So first of all, converting from our annoying basis to the standard basis. Right, so what do we do now? Well, that'll just be what we talked about before with the direct method. So what we do is we go down our vectors in the domain, our basis vectors. Right, and we apply t of this. Right, we apply t of this, and we find it with respect to basis c. Right, good thing is t is just the identity map. So all we're doing is finding 1 plus t with respect to c. And that's what we get over here, 1, 1, 0. Right, that's looking good. Same thing over here, we find the identity map here, find it with respect to basis c. And that's just from our direct method. Let's just remind ourselves this algorithm over here. Right, so we'll just do 2, 0, minus 1. Last thing we do is 0, 3, minus 1 from this vector, and we get this. So what we've done is we've just used our direct method to actually find the identity map that transforms from the basis b to a standard basis. And it turns out that with converting from an annoying basis to a standard basis, then that's really all we have to do. We just put our vectors down, we find the coordinate vector of each one, so 1, 1, 0, and then this one will be 2, 0, 1, this one will be 0, 3, minus 1, and what we do is just put them all into one matrix. So that's why we love this method, because it's so quick. All we have to do is find the basis and convert it to the standard basis. Next thing, the step we talked about, just finding the matrix representation with respect to the standard basis. So again, we've gone from the standard basis of P2R to the standard basis of R3. Right, so 1t squared, and then E1, E2, E3. Right, so what do? Well, it's exactly the same algorithm. So what we do is we take this basis vector, 1, let's do t of 1. Then we do it with respect to the basis in the codomain, which is S1. And they have over here, that's going to be equal to 1, 1, 0 with respect to S1. Why is that? Because we just calculate the constant polynomial. So 1 is just a constant polynomial, which means that its value at 1 is going to be 1. Its value at 2 is going to be 1. And its derivative at any point is going to be 0. So we get that. With respect to basis S1, we just get 1, 1t, because this is just a standard basis. So there's no real change. That's the first one. Same thing with t. Exactly the same process. We just calculate t of t. That's the second element in our basis. And that's going to be 1, 2, and then the derivative is always going to be 1. And then we get this and that. Final thing, we do the transformation of our squared function, the transformation of t squared. And what this means is we're going to have t of 1, t of 1, sorry, not t of 1. It's going to be t of t squared. That's going to be equal to the value of the map at 1, so 1, then 2 squared, then the derivative, which is going to be 2t. And we evaluate that at 2, so p prime 2 is going to be 4. And so we'll get 4. And so that will be tt squared. So we've gotten all these things, now we can put them in a line, and we make those the columns of our matrix. So we'll get 1, 1, 0, 1, 2, 1, 1, 4, 4. So from before, 1, 1, 0, 1, 2, 1, 1, 4, 4. Alright, final thing, convert back to the basis that we, the complicated basis, so C. Right, and so for this, what we want to do is, well, what we'd have to do using the direct method is we'd have to find the coordinate vector of E1. So first of all, let's go through the direct method. We calculate the identity map, so E1, with respect to basis C. So we calculate E1 with respect to basis C. That will be 1, 0, 0. That's not actually too hard. But when we go to do E2 with respect to basis C, well, that's actually pretty simple too. But then when we go to E3 with respect to basis C, we'll try to find this thing, so 0, 0, 1, with respect to this basis. And that's a bit difficult. So instead of doing that, what we do is we say, from before, if we wanted to convert from basis, an annoying basis like B to S, it was just the same thing as putting the coordinate vectors down. That was step 1. So we'll just put the coordinate vectors down. We'll get 1, 1, 0, 1, 2, 1, and then we had, sorry, that's the wrong one. We just put our bases down there. So we just put 1 plus t is 1, 1, 0. Same thing with 2 minus t squared. We'll get 2, 0, minus 1, and all the way down. So it turns out that converting from an annoying basis to C is always quite simple. Right? Now we want to convert from CS to an annoying basis. That's the other way around. So we might try to do it by the indirect method, but we realize that what we can do is because from before, so remember our property from before, if we want to convert something from one basis to another, and then we want to convert it back, we just take the matrix inverse. So what we'll do over here is just find the matrix that converts C to S, and that'll just be equal to the coordinate vectors placed as the columns. So over here we have 1, 0, 0, then we have 0, 1, 0, then we have minus 1, 2, 1. Right, so that's the coordinate vector converting from C to S. Right, so to convert from S to C, we'll just take the inverse of that. Right, so putting all the steps together, we get this. So we get 1, 0, minus 1, 0, 1, 2, 0, 0, 1, the inverse of that, which is what we just had. Then we have this matrix, so T with respect to B and C. And then we have the first matrix we calculated. And that's our full matrix. Right, so we'll move on to invariant subspaces. So the idea is that if we have a subspace of vector space V, so X, if we calculate T of all the elements of X, so we take X as an element of X, and we calculate T of X, it might not be an X, because X is a subspace of V. This is X, in a way, and this is V. Right, so if we do T of an element over here, it might be over there, for example. Right, map this to that. Right, so the idea is that this isn't guaranteed to happen, but if T of X, right, which is the subspace gotten by applying T to all the elements in X, so if T of X is a subspace of X, which means that all elements in X map back to X, then X is called an invariant subspace. So X maps back to a subset of itself. So what we're doing over here is we're showing that W is invariant under T, given that W is kernel S of S minus T. Right, so what we want to do is show that if we have any arbitrary element in W, then T of W is inside W. Right, because that means that whenever we apply T to any element in W, it always finds its way back into W. Right, so this is our main goal. So T of W needs to be an element of the kernel of S minus T. Alright, so what we'll do now, to show that anything's in the kernel, we'll have to apply S minus T to this thing. And if we can somehow show that this is equal to 0, then we've shown that T of W is in W, which means we've shown that this is invariant. Right, so what we'll do is we'll do that. We'll apply S minus T to T, and we've gotten this. So they tell us that ST is equal to TS. So if we flip these around, maybe we'll get somewhere. We'll get to what we want. And if we flip them around, we get TSW minus T squared W. Right, and what we can get from there is we can actually just expand this out, and we get this. Right, so we've applied this to T, and we've expanded it out. And now we're going to use our property. We're going to use our property ST equals TS. So we've gotten TSW minus T squared. Right, so that can be written out like this. And now what we notice is that when we think about it, W is in the kernel of S minus T. That's what we started with. So W is in W, and we're trying to show that T of W is also in W. So what we know over here is that this thing over here has to be 0, 2. Right, and that's where we're going to go with this. So this expression is equal to T of 0, and that's equal to 0. Right, so in other words, we've shown that S minus T of T of W is also equal to 0, which means that we've shown that this thing is invariant under T. We've shown that it's also in the kernel, right, so it maps back to a subspace of itself. So then we'll move on to a concept called similarity. Actually, because of time, we might not cover this, but we will cover similarity later when we talk about the Jordan form. Right, so that'll be next seminar. So what we'll do is we'll move on to something called the inner product and the dot product. So let's take the dot product, and this is from first year. Right, we have any two vectors in Rn. Take the dot product. That's going to be equal to 2 plus 6 plus 12. We multiply them component-wise. So 2 plus 2 times 3, which is 6, plus 3 times 4, which is 12. Right, so then we get 20. Right, so that'll be the dot product. We want to extend this to the complex space. So it's really important that we know this complex dot product. Instead of wanting to take just the component-wise products, let's just take an example. We're not going to just multiply them together. What we want to do is take the conjugate of all of this first. Right, so what we'll do instead is we'll say, let's take the product over here, but instead of just multiplying them, we'll make this the conjugate. So we'll say this is going to be equal to 1 minus I times 4 plus I. Next thing we'll do is we'll find the conjugate of this. This is 2 plus I times 5. Then we'll find the conjugate of this one, 3 minus I times 2. Then we evaluate all of that, and we'll get our dot product. The whole idea is that instead of just multiplying them together, we'll take the conjugate of the first one, then we'll multiply it by the second. So that's how we get this. So x dot y equals the sum of all x1 conjugate times y1, or xi conjugate times yi. So if the dot product is equal to 0, so remember this from first year, then x and y are called orthogonal. So it turns out that when we talk about dot products and complex dot products, that's all a type of inner product. It's a type of a broader concept called the inner product. Right, so the inner product is defined as a function that maps two elements. So we remember from the dot product it maps x and y, and it converts that to a single number. So same thing, we want an inner product that maps two elements, so v times v, maps it to the field, so just a single number, and that will be denoted by this. So x, y, that's called the inner product of x and y. Alright, so now what we want to do is just go through the properties of inner products. So we need to have linearity in the second component. What that means is that if we have x inner product with y plus z, then we actually take the inner product separately and add them together. Also, if we have a scalar in here, we can take that scalar out. Right, so this is called linearity in the second component. Right, so we've got linearity in the second component. The other thing is that we have conjugate symmetry. So what that means is that if we want to switch them around, we'll get the conjugate. Right? If we switch them around, we'll get the conjugate of what we had originally. That means that we can't just switch them around willy-nilly, we have to consider the conjugate space. So sometimes we have an inner product defined over R. It means that we don't have any complex numbers, which means that we will have xy equals yx. Right? Because the conjugate of a real number is just the same thing. So we'll just get x comma y. That's going to be equal to y comma x. Only in the real product space though. The final thing is called positive definiteness. So if we take an inner product of a vector with itself, it's always going to be greater than or equal to 0. And it turns out it's only going to be equal to 0 if both of these things are 0. Right, so that's our final property called positive definiteness, and that's what we need for an inner product. So we're going to talk about another property of inner products, so orthogonal vectors. So if we have this inner product is equal to 0, then they're called orthogonal. When we denote this as x, we've seen this as perpendicular, but we can extend this to orthogonality. X is orthogonal to y. And the other thing is that if we have a set of vectors, and they're all orthogonal with each other. So let's just take this set, vi from I equals 1 to n. So v1 all the way down to vn. So this set is going to be orthonormal if we have two properties. So the first one is that they're all orthogonal to each other. So v1 dot v2 will be equal to 0. v1 dot v3 is going to be equal to 0. In other words, if we have this inner product of v1 with vj, then it's going to be 0 if they're different vectors. So for example, v1, v2 is going to be equal to 0. Same thing over here. If we have them being v1 times v3, that's going to be equal to 0. And that's our first property. So this is called orthogonality. Next thing over here, we need all of them to have an inner product of themselves. So v1, v1. This is going to need to be equal to 1. Right, so for example, we're going to have v2 is going to be equal to 1. Right, so this is a property of orthonormality. Right, so we're talking about the idea of a projection. So when we have two vectors, so x and y, so not all vectors actually look like this, but this is just a geometrical representation for us to get our head around. So we have x over here, and we have y down here. If we want to project x onto y, then we might have seen this diagram before. What we want to do is kind of find the shadow of x on y. So over here, we'll take this. X is projected onto y, we'll get something like this. Right, and so the way we do that is we take y, so that's this thing over here, what we're projecting on, and we multiply it by its inner product with x, and we divide it by its inner product with itself. So this thing is just going to be a constant. That's why we have this diagram, right? That's why we have this diagram where the projection over here is going to be some scalar multiple of y. Right, so that's what we have down there. So the formula is defined so that we have this really nice property, which is that x minus the projection of x on y is going to be perpendicular to y. So let's take this. So this is the projection again, which means that x minus the projection is going to be this. Right, so this vector is going to be perpendicular to y. So that's why we use this formula, because we have this formula where x minus the projection of x on y is orthogonal to y. So we have to note that the order of the numerator is going to be important. So don't do x comma y, because in complex inner products we don't have symmetry, right? So we have conjugate symmetry, which means that the order is important. So we always have to have y, x. And to remember this, we know that the projection of x on y is written like this, and the order stays the same in the top. So we have y, x. So in both cases, x comes second. Right, then we divide it by this. Right, so it turns out that any finite dimensional inner product space has an orthonormal basis. Right, so this is using the Gram-Schmidt process. We know that any finite inner product space has an orthonormal basis. Right, which means that we can always find some basis that is orthogonal, and where the inner product of every single vector with itself is going to be 1. So what we do is we do this simple procedure. We can convert any finite basis using the Gram-Schmidt process to transform it into an orthonormal basis. So what we do is we say, let's start with v1 all the way down to vn. And we're going to work our way down into transforming this into an orthonormal basis. So what we'll do is we'll say the first vector of our new basis is going to be w1. And first of all, we're happy with this first vector, we'll work with this, and we'll let this be equal to v1. Then what we'll do is we'll say, let's take the second element, but when we think about it, v2 isn't necessarily going to be orthogonal with v1, right? So v2, v1, v3, this is just a basis. We have no guarantee that it's going to be orthogonal. So what we do is we say, we'll take v1, but we can't take v2. So w1 all the way to wn is going to be our new basis. We can't have v2 in it, right? Because we don't know if these two things are orthogonal. So what we do is we say, let's take v2, but let's subtract its projection onto this first thing. Right, so if you draw a diagram, then it becomes clear why this is orthogonal to it. But basically the process is we just take w2, and then we take the second vector over here, then we subtract its projection onto the first element of our basis. Then with w3, we take our third element, so v3, and then we subtract its projections onto these two elements of our basis. Right, so we're kind of constructing our basis as we go. So our first element of our basis will be w1, and that'll just be the first element. Right, then the next thing we do is we take W2, but then we take our second vector and we project it onto the first element of our new basis. Basically, we're making use of this new basis. Then the third thing we do is we take our third vector and we subtract its projections onto the previous two. And you can probably imagine that for our last element, so Wn, what we do is we take V of n and we subtract V of n's projection onto the other n minus 1 elements of our basis. And that's how we get this formula. Once we do all that, we're done. Right, so that means that once we do that, we've gotten an orthogonal basis, which means that W1 will be perpendicular to W2, or maybe let's use the inner product notation. W1 will be perpendicular to, or orthogonal to W2. W1 will be orthogonal to W3, and all of that. But we don't have the other property. We don't have the property where W1 is equal to 0. It is equal to 1, sorry. And we need that, so we're going to have to change something about this. Right, so what we'll do is we'll say, this thing doesn't have an inner product of itself with 1. So what we'll do is we'll take V1, and we'll divide it by its norm. Right, so we've gotten our new basis. Let's just draw this out. Sorry, I'll just erase all this. Right, so we've gotten our new basis W1 all the way to Wn. And what we're going to do is we're just going to say, we want the inner product of W1 with itself to be equal to 1. So we take W1, and we divide it by its norm. And what its norm is equal to this. So its norm is equal to the inner product of itself, the square root of that. Right, so we have W1, and we divide it by this norm thing. Right, and it turns out if we do that for all of our vectors, we divide W1 by its norm, we divide W2 by its norm, we divide Wn by its norm, then we'll always have an inner product of itself with 1. So once we have this nice basis, we just divide by this, and this process is called normalizing. Alright, so we'll put this into practice. Let's do the Gram-Schmidt process on these 3 vectors. These are our V's, and now we're going to try to find our W's first. Alright, so W1 is just going to be V1. We're happy with that. But we're not so happy with V2, because it might not be orthogonal. So we take V2, and we subtract its projection onto W1. Right, so that's V2 here. What we do is we take this thing, and there, and we subtract its projection onto W1. This is just our formula. Right, and then we can just evaluate all of that, and we'll get this. Right, so how do we, for example, do this thing on the top? We just do the inner product. And under the regular dot product, that's just going to be equal to the component-wise multiplication. It's going to be 6 plus minus 1 times 0, which is just 0, plus 0 times minus 2, which is 0, plus the last one, which is just 0. And that's what we get here. Right, so we do the same thing over here, and we just get our nice little W2. W3, we take V3, but we're not so happy with this one, we have to change it. So we subtract its projection onto each of the elements that we've gotten already. So remember we got W1 equals, what was it? It was just this thing. W2, maybe let's just write that over here. W2 was this thing. So a third times 5, 2, minus 6, minus 4. Right, so we subtract this projection onto these 2 vectors. Right, so then we get this. We collect all of that, and we should get this. So now we've gotten our first step, which is our orthogonal basis. But we still have to divide by the norm. You have to divide by the norm. And with a standard dot product, the norm is just equal to the magnitude of the vector. So then we just, for example, over here, we can divide by the magnitude of this, which is root 2 squared plus 1 squared plus 2 squared, which is equal to 3. So we divide this by 3. Same kind of process over here, and we get our orthonormal basis. So remember our two properties. So vi, vj equals 0 for two different vectors. And also v1, v1 equals 1, which is to say that v1 the norm of v1 is equal to the square root of 1, which is just 1. So those are our two properties here. So number 1 up here, and number 2 down here. Okay, so we'll talk about the orthogonal complement. So when we have a given vector space, so let's say, for example, we have a nice little plane, or a nice little line. Let's just start with a line. So this is an R3, and we have a nice little line. Oh, that's not a good line. It should be through the origin. Right, so we have this nice little line. What is the orthogonal complement? Well, the orthogonal complement is the space of all vectors in this entire vector space, such that it's perpendicular to all vectors in W. So if W is our line, we need vectors that are perpendicular to the line, no matter what point in the line. So in this case, that will be a plane, for example. It will be the plane that this line is normal to, right? Because then if you take any vector in this plane, will be perpendicular to the line. And that's what the orthogonal complement is. It's a space of all vectors such that xy equals 0 for all y in the original space. So in this example, we'd have w equals the line, and then we have this equals w complement. And so we have a theorem that w, the direct sum of w and w, the complement of w, equals the entire space. So what that means is that if we have any vector in x, so any vector x in V, as long as it's finite dimensional, right, so for any finite dimensional space, this is true. If we have any vector in a finite dimensional vector space, then it means that x can be written as some vector from W plus some vector in the W complement. Right, so in this plane example, it means that if we have any vector up here, so let's just say we have a vector randomly up here, then we can express it as a sum of the orthogonal complement, so something down here, plus something that's normal to the plane. And that will look a bit like this. Right, and so this is going to be our theorem. And so it turns out if we have this representation, if x is equal to a plus b for a in W and b in W complement, then it means that a is going to be the projection of x onto W. Right, so that kind of makes sense, right? Because when we look at this diagram, this is A. This is B. And this is A. So A is the vector in W, and B is the vector in W complement. Right, so it means that this thing is kind of like how far we get with A in W complement. Right, and this thing is how far we get with in this vector space with W. Right, so it means that A, because A is going to be in W, is going to be our projection onto W, and B is going to be our projection onto the complement of W. And so this is a really important equation. We should use this whenever we're working with any projections. X minus the projection of x onto W is perpendicular to y for all y in W. Why is that? It's because when we think about it, x is going to be equal to its projection onto W plus its projection onto W complement. Right, so what that means is that if we take x minus this thing, if we've taken the W part away, then what we're left with is some element in, sorry, I'll just erase this, is we're left with some element in W complement. Right, so if we actually draw this out on the diagram, you have this plane here. I'll just use another color. So for example, we have x up here, x is here, and its projection onto W would be this thing. That means that if we take x minus its projection, then what this part is, it's the W complement part, right? It's the part that's in W complement, which means that it's going to be perpendicular to all y in this space. So it's going to be perpendicular to all these vectors here. Yep, so that's our complement. So if we are working with projections, we're always going to want to use this. So let's take an example here. We're finding the projection of a vector, f, onto W equals the span of these two things under a given inner product. So we're talking about projections, which means that we are going to use our all-important statement here. So f is kind of like, it's a polynomial, but we can still visualize it. This is like g1 and g2. And what we want to do is find the projection of f onto this span. So this is going to be that here. Projection of f onto W. Right, so in other words, we need f minus WH, so this is going to be h. So if h is our projection, then it means that f minus h, so this thing over here, is going to be in the complement. Right, so f minus h will be in the complement, which means it's going to be orthogonal to both g1 and g2. Right, so what we can do is we can say, let's let h, because h is in the span of g1 and g2, let's let this one be a1 g1 plus a2 g2. And so once we've set that, we can say f minus h is going to be orthogonal to both g1 and g2. Right, so in that sense, we might actually find out what a1 and a2 are going to be. And let's move on from that. Alright, so we've gotten this. So f minus a1 g1 minus a2 g1 g2 is going to be perpendicular to g1. Same thing over here. This is going to be orthogonal to g2. Right, so we write this out in a product because that might give us an equation. We'll get f minus a1 g1 minus a2 g2. Inner product of that with g1 is going to be 0. Same thing over here. So f minus a1 g1 minus a2 g2. The inner product of that with g2 is also going to be 0. Right, so because these are both in the orthogonal complement, they're going to be perpendicular to both g1 and g2. Alright, so we want to expand this to find alpha 1 and alpha 2. So what we do is we use the linearity of the real inner product. So we just write it all out. Alright, so we get rid of all of this. We get a1, a2, a1, a2. And we've gotten basically all of these g2s, g1s, g1s, f's inside these inner products. Right, so now what we can do is because we've separated the alpha 1 and the alpha 2 from everything else, we can just calculate these inner products. So let's do that. We'll calculate these inner products. And basically you just use the formula. They gave us a formula for the inner product. It's P0, Q0, P1, Q1, P2, Q2. So for example, for f of G1, right, what we do is we just calculate P of 0 at f, which is going to be 3. Right, so we get 3 here. Same thing up here, we'll get Q0. Q0 in this case will be just G1 of 0. And g1 is going to be equal to 1 minus g. So that's going to be 3 times 1. Right, same thing we'll do at P1 and Q1. We'll just evaluate them at 1, and we'll get this. And we'll move on to that. And that should give us minus 4. And we'll do that for all of them, and we'll get all of these numbers, and then we can just sub them in. So remember that these were just coefficients to plug in. So we just plug them all in, we'll get this nice linear equation. We'll get this. So from then what we can do is just find out what alpha 1 and alpha 2 are going to be, and then that will give us the projection. Because remember, we defined our projection as h equals alpha 1 g1 plus alpha 2 g2. Right, and so we just sub that in. We sub in minus 5 g1 plus 3 g2 equals this thing. And that's our projection. So we'll move on to the QR factorization. The QR factorization is just a way of expressing a matrix, so A1 all the way down to AQ, as a product of two other matrices. So A will be equal to QR, where Q is going to be the same size, but it's going to be an orthogonal matrix. So it's important to realize that these two things are going to be the same size. So A is going to have the same size as Q. The only difference is that this will be an orthogonal matrix. So orthogonal matrix means that these columns are going to form an orthonormal set. Alright, so now what we can do is we can express this as equal to this times an upper triangular matrix. And this is just our R. Let's try that out. Alright, and it's just going to be this size. It's just going to be a square matrix that is invertible and upper triangular. So it's just a way of expressing this matrix as a product of an orthonormal matrix and a nice upper triangular matrix. And so our formula for this is just by doing the Gram-Schmidt process. Let's take a look at this for a second. We know approximately what our matrix looks like. What we just do is we take the columns of A, so let's let our columns be A1 down to A2, all the way down to AQ. If these are our columns, then what we do is we just use the Gram-Schmidt process on these vectors. So A1, A2 down to AQ, we just use the Gram-Schmidt process on that. Right, and what we'll get is we'll get orthonormal vectors. We'll get Q1 into Q2, all the way down to QQ, multiplied by all of this. And all we do is we just sub in the values that we got from the Gram-Schmidt process. So we remember from the Gram-Schmidt process, first of all, we find W. W is the set in the orthogonal set. And Q is what we get once we normalized it. Right, so what we have is W1 all the way down to WQ as the diagonal. And then we'll have all of these inner products. Right, so all it really is just subbing in values into our matrix. Right, so once we have W, our orthogonal set, and Q, our normalized set, so our orthonormal set, we can just sub it into this matrix. We'll skip through this, we'll just move on to the example. So we have B, and we want to find the QR factorization of it. So this column will be our first vector, so 1, 2, 0, 2 will be our first vector. Our next one will be 2, 1, 1, 1. Then we'll have 1, 0, 1, 1. Right, and the idea is just that we want to use our Gram-Schmidt process on these three vectors. Right, so we'll do that now. So our first one is just this, W1. And what we'll do instead of what we did before is we'll normalize our vectors as we go. Right, so let's just think about this. We'll normalize our vectors as we go, which means that as soon as we find W1, we'll find Q1. Right, so we found W1 now. Usually we just move on to V2 we just move on to W2. So we'll just move on to W2 equals V1 minus the projection of V1 on W1. V2. Usually we just move on to that. But in this case, what we're going to do is just normalize this immediately. So we'll divide it by its norm, which is 3, to get this. And the reason why we do this is because now what we can do is we can find W2 using its projection onto Q1. Right, so now we're using this as our V1, so to speak. This is like our new vector to use. So what we do is we take our second vector. Our second vector is 2, 1, 1, 1. We take 2, 1, 1, 1, and we subtract 2, 1, 1, 1's projection onto this. And it turns out that that actually makes things a bit easier, because now what we do is let's just write this out, projection of this to Q1. That's going to be equal to the inner product of Q1 with 2, 1, 1, 1 divided by Q1, Q1 times Q1. Right, so let's look at this. The cool thing about this is that it's a lot easier because now we get this thing up here. And this thing was actually an element of our R matrix. Right, so if we normalize as we go, we get the elements of our R matrix for free. So we get this now. And this thing as well is just going to be equal to 1. Because remember, Q is orthonormal. So in other words, we can just take the projection here and we multiply it by Q. Right, so we get 2, we multiply by Q2. Right, and so we get this as well. But the important part is that now we have our inner products already. We have this thing here, and we're going to use that in our matrix later. Same thing with W2, we normalize that first to get Q2 immediately. Then what we do is we take W3, we do the same process, we subtract its projection onto Q1, then we subtract its projection onto Q2. Right, and it's the same process. Because it's a projection, we don't have to worry about any denominator because Q1, Q1 is just going to be equal to 1. Right, so now we have our nice little formula, and we can move down. Now we've got W3 is equal to V3 minus its projection onto Q1 and Q2. So we get this and that, and we get that and that. And so again, these inner products will form the basis of our R matrix. So let's just put them aside and we'll keep them here. The next thing we'll do is we'll look at W3. So W3, the same thing. We find its norm and we divide it by that norm to normalize it. Right, so now we've gotten all of our inner products, we've gotten all of our orthonormal vectors. So now we do Q, which is kind of the easy part. All we do is we find our Q1, Q2, Q3, which we just calculated, and we make those the columns. Then for R, remember that these things were the diagonals of our formula. So we had W1 up here, then we had W2 down here, then we had W3 down here. Right, so we're going to get that. So that's why we have 3, root 2 on root 3. Right, because we have W1 equals 3, this equals root 3, and this equals root 2 on root 3. And then what we can do is, because we've already done so much, what we can do is we can find the inner products with Q1 by looking at our Gram-Schmidt process. So remember what we had over here. We had W3 equals this thing minus the projection onto Q1. And so we ended up with 1 here. Then we ended up with 2 on root 3 here. So what we can do instead is we can take this column. So this column corresponds to W3. And we can just say these things will represent these inner products here. So 1 goes down here, and 2 on root 3 goes down there. Right, so this is just the expression for W3. And we get these two nice little inner products. You can probably imagine where 2 comes from. 2 comes from our previous equation, where we found W2, using its inner product with Q1. So we had this thing, this is 2, and so that's why we have that down there. So just to recap, what we do is we find our diagonals first, using the norms of each of our W1s, and then we can go back to our Gram-Schmidt process and look at the coordinates down here. And we'll get this as well. And so to recap, our QR factorization is just going to be this times this. Alright, so because of time, we might just look at one more thing, which is the adjoint. So what is the adjoint? The idea is that what we're doing is we're finding the inner product of W with a transformation of T. And what we can do is we can just find a function such that if we just remove this and replace it with something down here, the inner product will be the same. So consider the linear mapping T. There is a unique linear mapping from W to V So our mapping is from V to W, and our adjoint will be from W to V, such that W times T of V is equal to the adjoint of W times V. Right, so we just move this function down there. Right, so what we can call any such T, the adjoint of T. Right, so there are some properties of adjoints. Basically, it's if you have a sum of two functions, the adjoint is the sum of the individual functions. The individual adjoint, sorry. If we multiply by a scalar, we can just take the scalar out and take its conjugate. And the adjoint of an adjoint is just the original thing. This property as well, we have U composed with T, the adjoint. It's kind of like the inverse. What we do is we just reverse the order. You get T adjoint composed with U adjoint. So we'll do an example. So consider the following linear mapping from R2 to P1R defined by this. And what they've given us is one inner product on each space. So the standard inner product for R2, and they've given us an inner product for P1R. That'll be equal to P0Q0 plus P1Q1. So remember our formula. We want, for any two vectors, P times, actually we'll use X and Y. The inner product of X with T of Y. What we want is we want the formula such that we get this. We move the adjoint back here, and we have a Y up here. Right, so we want a function that satisfies this property. So because we don't know this just yet, we're trying to find it. Let's just calculate this thing first. Let's just calculate X and the inner product with T of Y. Actually, yeah, we'll do this. So we've got an X over here. We've got an X down here. And we've got an arbitrary P. So what we'll do is we'll find the inner product of P with T of X. Different from there, but it's just going to be P times T of X. And the reason for this is because T maps R2 down to P1R. Right, so the idea is it maps some elements x1, x2, and then maps it to a polynomial. Right, so that means that when we do calculate this expression, so P T of X, they're both going to be polynomials. So we'll say x1, x2 is going to be this, and pt is going to be this. So now that we're in P1R, we'll use the inner product on P1R. So all we do is we calculate P0. So P0 for this thing is just going to be P0. And Q0 over here is going to be the transformation of this. So the transformation, first of all, we do this. That's going to be equal to x1 plus x2 minus 2x2 times t. Right, and p of 0 is just going to be this constant term. So that's why we have x1 plus x2 times p of 0. And we can do the same thing over here. We just do p1 times q1. So we evaluate p1, and that's going to be p0 plus p1. Then what we do is we do the same thing with this polynomial. And we calculate it at 1, so we get x1 plus x2 minus 2x2. So that'll be x1 minus x2. So now we have that this inner product is going to be this. So remember the question that we're asking is, what do we have to do to p such that we have this? Remember this property? This will be t, p, x. So what do we have to have this be such that this equality will hold? Well, the idea is if this thing is down there, we want some function of p such that if we multiply x1, so remember the dot product, so we're using the dot product here, x1 times something plus x2 times something else will be equal to this thing here. Right, so this thing is going to be our expression. And the question we're asking is, what do we have to do? So what is the adjoint going to be if it's dot product with x, so x1 times something, plus x2 times something else, is going to be equal to this. So what we'll do with this expression is we'll separate the x1s from the x2s. So let's do that. And we expand it out. So because of time, we'll just skip through this, but basically we just get x1 times this thing, just collect all the terms with x1, then collect all the terms with x2. And so we'll get this expression equals the dot product of x with the adjoint of p. So what that means is that when we think about it, this is just equal to x1 times the first component of t adjoint p plus x2 times the second component, which means that this thing is the first component and this thing is the second component. So we've got our adjoint equal to this, and that's our formula there. So just remember we want to solve this expression, so something in the form of this, depends on what the vector is, will be equal to t adjoint y, x. Once we do that, we'll try to find which formula for t adjoint is going to satisfy this property. So we'll cover one last thing. So unitary and hermitian linear maps. So unitary and hermitian linear maps. So remember the adjoint. The adjoint is just a transformation. And we had this property where when we go from v to w, then the adjoint basically takes us back. It takes us from w to v. And the idea is that if we have a linear transformation that goes from v to v, so the codomain is equal to the domain, then t is unitary if it's called self-adjoint. Which means that if you actually take its adjoint, then it's equal to, that's hermitian. So t is unitary if its inverse is equal to its adjoint. Right, so that's the concept of unitary. And for hermitian, it's going to be self-adjoint. Yeah, so it's going to be self-adjoint, which means that the adjoint of t is going to be equal to t. So that's the idea of a unitary and hermitian linear map, because when we go from v to itself, then the adjoint will also be from v to v, which means that we have the possibility that t adjoint is going to be equal to t. And so there's this definition. So a linear transformation is called an isometry if when we take the transformation of v, it's going to have the same length as v. Right, so for example, if you have the linear transformation equal to minus v, then you might be able to see that this is always going to preserve distances. So it's always going to preserve this. When you transform v, its distance won't change. Right, so we have, in other words, we have t of v has the same length as v, which means that we'll have an isometry. And it turns out that we have an easy way of knowing when something's an isometry. It's an isometry if and only if it's unitary. Right, so if something is unitary, which means that if its inverse is equal to its adjoint, then it's going to be an isometry as well. Right, so that's how we show something's an isometry. So we'll possibly do one last question. So let this transformation be defined by t of wz equals this thing here. So is t unitary, or is it isometric, or is it hermitian? So for this, we'll actually use a shortcut that we know. So what we could do is find the adjoint using our dot products. Right, so before we found the adjoint from first principles, basically. But in this case, we have something from C2 to C2, and it's defined by this. Right, so in other words, this is a linear transformation between C2 and C2. So it turns out that when we do have this, there's a simple shortcut we can use to find the adjoint. So if we have t of x equals a of x, then if we want to find the adjoint, what we do is we take the conjugate transpose. And what that is we just take the matrix. So let's just say we have something like 1 plus I, 2 plus I, 2, 3. The conjugate transpose is just, first of all, take the transpose. Let's take this. So we'll skip this around. We'll get 1 plus I, 2. And then we'll get 3, 2 plus I. Then what we do is we take the conjugate. So we get 1 minus I, 2 minus I, 2, 3. So what that means is that this will be the conjugate transpose. So AT, conjugate. Right, so it turns out that this is a really simple formula for the adjoint. And because of this formula, we can actually just write A transpose, the conjugate of that, equals A adjoint. Right, so the adjoint of A is equal to the conjugate transpose. Right, so it's important to note that this only works if we have a transformation from Cn to Cm under the standard inner product. So again, we could calculate the adjoint from first principles, but we'd rather not. So let's do this over here. So Tx equals 0 minus 1, 1, 0 times x. And the cool thing about this is that we're just using what we did before. Right, so if we have T of Wz equals minus Z, W, then we just take the coefficients of each term. So minus 1 would go down there and become there, and 1 over here would go down there and become that. So we have 0 minus 1, 1, 0. So we take the coefficients of W and Z and make them into a matrix. Right, so now what we can do is we can find this transformation, A. So A equals 0 minus 1, 1, 0. So then the adjoint matrix is just going to be the conjugate transpose. So take the transpose first of all, we get this. And because everything is real, we just stop there, and this is our transpose. So in other words, if we want to write out our adjoint, we just get this. So T adjoint of x equals 0, 1, minus 1, 0, x. And that'll be our adjoint. Okay, so now we can go on to proving whether it's a unitary or isometric or hermitian. So for a unitary matrix, we need A adjoint equals A minus 1. So the inverse of A is equal to its adjoint. So what we can do to prove that is we can just calculate A times its adjoint. And if this is equal to the identity, then, well, they are inverses. So let's do that. We get 0 minus 1, 1, 0, times 0, 1, minus 1, 0. Remember, A was just our matrix here, and the adjoint of A was just this matrix down here. And that turns out to be equal to the identity matrix. So in other words, it is unitary. Yeah, so it's unitary, which means that T is a unitary transformation. So from the previous theorem, we also know that all unitary transformations are also isometries. So T is also isometric, which means that if we apply this transformation, T of V, its distance will be equal to just the distance of V. So that's how we get that. Final thing, for a hermitian transformation, we need it to be self-adjoint, which means that A is equal to its adjoint. But when we look at this, we see that this is A, and this is the adjoint of A, and they're clearly not equal, so the transformation cannot be hermitian. What we'll actually do is we'll move on to one last thing. I'll just cover this because it's not too long. The method of least squares. So sometimes you want to solve a system of equations, but you don't really have a solution. So for example, if you have a system like this, then it might not be solvable. Because you can see you have so many equations. But you only have 2 parameters, right? So the reduced row echelon form might look something like this. And you might have something like this on the end. It's just an example. This is not actually the row reduction. But the point is that sometimes you can't solve an equation. Sorry, I missed the eraser tool. Okay, so if you can't solve the equation, the best you can do is find the closest solution. And that's what's called the least squares solution. So we have this equation ax equals b, and there's no solution. So what we do is just multiply by the adjoint of a on the left. So for Math2501, we just use AT because we don't talk about adjoints, we just talk about the transpose. So we just do this. Either way, we just multiply it by something on the left, and we'll get something that will be solvable. So find a parabola that best fits in the least square sense to these points. So let's just think about what that means. We're trying to find a relationship like this. Y equals a plus bx plus cx squared. And remember, this is x, this is y. So what that will mean is that we have y equals a, or will be this, but then we apply that to these 3 points. So we'll get 6 equals a minus b plus, sorry, that should be an x, a. Then we'll have another equation here. 2 equals a plus b plus c. We'll have 3, we'll have minus 1 equals a plus 2b plus 4c, and so on. The idea is that we'll have 4 points, but only 3 parameters, which means we'll have to use this least square solution. So first of all, write down the system of equations we're trying to solve. Right, so this is y and this is x, which means that we should have 6 equals a minus b plus c. Right, so this will be 6 equals a minus b plus c. That's our first one. We do that for all our points, so we get 2 down here, minus 1 down here, and 7 down here. Then what we do is we just put in the numbers that we're solving in. So this will always be 1, because a is always multiplied by 1. This will be equal to x, so there will be 1 over here, 2 over here, 2 over here. And this will be equal to x squared. So this will be equal to, over here, we have minus 1 squared, which is 1. Then we have 1 squared, which is 1. And 2 squared, which is 4. And 2 squared, which is 4. So now we've gotten our solutions. And already we can see that this is an augmented matrix that might not have a solution. So what we do now is we multiply both sides by the transpose, or the conjugate transpose. So we've gotten this, and we multiply by that, and we get this matrix. Then what we do is we do the same thing on the other side. So remember, ax equals b, and to find the approximation to that, we just do a asterisk a times x equals a asterisk b. Alright, so now we've gotten that this times x will be equal to that. And again, this is looking a lot better, because we only have 3 rows now. And in general, when we do this, we'll always have the right number of rows. So now we've gotten this, we've got this system of equations. Reduce, reduce. And then we can just find a, b, and c. And just keep in mind what you defined a, b, and c to be. So for example, over here, c is our coefficient of x squared. So when we have this thing here, so 3c equals 3, we know that this thing will have to be 1. Same thing up here, we use this equation. This is an equation for 6b plus 6c equals minus 6. Right, so then we can find b and c. And so what we do is we just find out what a, b, and c are, and that'll give us our least square solution. Right, so it doesn't matter whether it's a line or a parabola or even an exponential fit. All you really have to do is find the equations that you're trying to solve for. So for example, you sub in x, you sub in y, and then you can find out your parameters. Right, and that's how you do a least squared solution. Right, so that's basically everything that we've covered. So we've covered linear transformations and inner products, and we did go a bit over time, so sorry about that, but there was a lot to cover there. What we'll do is next seminar, we'll cover the rest of the course. So that will include everything after inner product spaces. All right, and so that will be taken next time. Yeah, so thanks everyone for coming. If you have any questions, feel free to pop them into the chat. But that's the end of our seminar for today. No worries, that's good to hear.